Good morning. Thanks for attending. It's the last day, and yesterday was the party, right? Okay, I hope everybody's still alive. This is about garbage collection. Who's a Java developer here? And even if not, many of the principles work in other languages too. My name is Gerrit Grunwald. I'm working for Azul, as you can see, and we do JVMs. So everything related to Java and JVMs, this is what we do. If you would like to reach out to me, just ping me on LinkedIn. That's the easiest way. If you have Blue Sky, then you will find me under hansolo.au on Blue Sky. No Twitter anymore, sorry. All right, that should be it. We just have 40 minutes. Memory management in the JVM. It's automatic, right? So I care. That's it. You did it. So, yeah. So I saved you some time. Who is specifically setting a garbage collector in production here in the audience? Okay, a few people, which is fine. The rest just use the default. And it works? That's great. That just means everybody did a great job. Anyway, you should at least have some knowledge about garbage collection. Most of you heard it during the studies, and then, yeah, there's something. But you forget about it because you never use it, which is fine. But it has an impact on application performance, responsiveness, and requirements like memory and CPU usage. And this is just the least things you should know. But to give you a little recap how it works in the JVM, so we have a stack, right? And this is for each thread. And in that stack, we have stack frames. Right? So, and then for each method that will be called, there is a new stack frame on that stack. And that is for each thread. So, and we store primitives and references in these stack frames. And that means that we have the heap. And in the heap, we have the actual objects, right? They take up the memory. And there we have out of memory exception where we have stack overflow on the stack frames. And then there is the so-called metaspace where we have class metadata, constant pool, code cache, and so on. But this is not really relevant for the stuff that we talk about today. So we just talk about these two things. So stack frames and heap. And to give you an idea, and this is what I meant, I hope it's readable in the back. The screen is not the biggest. I have a record person. I have 4 instances of that, and I put them in a list. And I just print out the name of the first one, which is mine, which is easy peasy. Then we have a thread for that method, or for that program, and then we have the stack for that method, the frame, and we see we have the references for the 4 persons and the reference for the list, okay? And then we have the heap, and these references point to the objects on the heap. This is how it works. And you see that the list has an internal reference to these objects, right? Because it keeps a reference to the objects. So that means all these objects are reachable. And if I say an object is alive, then it means I can reach it from the stack frame when I follow the reference into the heap. I can find it. And that's important. So that means if I set the P1 to null, right, then you would think, okay, that's gone. I can't reach it anymore. And this is true if you print out system.println P1, result is null. But still, and this is sometimes a problem for the younger developers because they just simply don't know, the list has an internal reference to the same object. So if I do something like persons get 0, I will still get my name. The object is still there, and it's still reachable via this internal reference, okay? And this will stay until I set the persons, the list to null, and then the reference is gone. And then I only can reach these 3 objects in the middle, and the rest is garbage. Means it still takes up space on the heap, but I can't reach it anymore. Okay? So how to get rid of this stuff? Garbage collection. That's the idea. Just to give you an idea how it works and why we do it. Garbage collection in general is a form of automatic memory management. There is also something like automatic reference counting. This is, for example, done in Swift. It's in principle another way of doing it, also has advantages and disadvantages. It's just we do garbage collection in the JVM, and it's an automatic form of doing that, and it's a way to identify and reclaim no longer used memory, right? The stuff that was garbage there. And it ensures efficient memory utilization. The biggest point is it gives you the freedom that you don't have to do malloc and free. Do we have people with a C background here? And you love it, right? Yeah, I know. It's back in the days. So, to give you an idea how it works, we have to talk about phases, and therefore we just focus on precise collectors, because there's also something like, I always forget the name, conservative collectors, but we just have precise collectors in the JVM. And we have phases there. We have the so-called tracing phase. So you will see this a couple of times in this presentation. This should be the heap. The gray stuff here is memory cells. If they are blue, they are used, they are live. If they are purple, might be hard to see, then they are dead. So that means no reference is pointing to it anymore. And they sometimes have a little red square in the upper left corner. That means they are marked by the garbage collector. So the little white squares on top, this is the stack frames. I will try to use that every time. When you see white squares, this is the stack frames with references pointing into the heap to the objects, okay? So tracing means we have to find everything that is live. So that means we follow simply the references from the stack frames, find the object, mark it, okay, this is live. Go to the next one, find it, mark it. This is a two-step process. Finding, then marking, right? And same. Finding gives this little gray square, and then if it's marked, it's red. And then the same for the last one. Okay, so now everything that was live or is live was found by the tracing phase. Now we would like to free the heap from the stuff that is not reachable. And you might already get the idea this is not so easy because we don't have references to follow. How can we find the dead ones? Well, the simplest approach is going through every memory cell and check if it's live or not. And this is exactly what happens, right? So that takes some time to go through the whole heap and check for all dead cells and remove them. So that means freeing is not for free in this case. There are other approaches we will see, but in this case it might take some time. The bigger the heap, if we use this strategy, freeing takes long. Okay? So, yeah, and then we have to unmark until we freed all objects, we unmark the live cells, and that's like a reset. So then we can start over again. The next one is compaction. So because you see it's cluttered, right? We have some objects are used and other cells are free, but it's not always continuous space. To make it a one continuous space, we have to compact. In this way, I will try to move everything to the upper left corner. That means we take an object, move it to the next position. The reference is still pointing to the old position, so that means we have to update the reference, right? So we update the reference to the new one, an additional step. If we do compaction, that means updating references is an additional step. And then we do that for all the objects, and now it's clean and compacted. These are the three phases when we talk about precise collectors, right? And all of the collectors share, in principle, these three phases. It's always tracing, freeing, compaction. But we will take a closer look how it works in reality. Who knows what stop the world means? Okay, everybody that doesn't know, it's not a problem. It just shows that we did a good job over the last 10 years, because 10 years ago, everybody knew what it is. Stopping the world means, if you have the JVM, and we saw already there's the heap, and we have to clean it up, that means if the JVM starts to clean it up, you can't simply continue allocating memory, right? So therefore, you have to stop the world. That means stopping all threads, and then do the garbage collection. So that means we have application threads running, then the JVM sends a safe point signal, and then it will lead to the fact that all the threads will go into a safe state. That's a so-called JVM safe point. And at that moment, the application literally stops working. It looks like it hangs. It doesn't, because now the garbage collector steps in with one or multiple threads, cleaning up the heap. Once this is done, it restarts the threads and everything continues working, okay? The whole idea of, because we have all these different garbage collectors, the whole idea is to make this gap as short as possible. Because that leads to the fact that in the past, you could find applications that stop for seconds. Nothing works. And then suddenly continue. This is a garbage collection pause, right? So this is the reason why we have different garbage collectors in the JVM, because over time there have been different principles that work more or less better for different use cases. Collectors, I don't mean the collectors in the JVM. This is basic garbage collection principles, and probably you heard some of them. Mark and sweep, who heard it? Heard about this? Probably all of you. Who knows how it works? Don't be shy. Yeah, not a problem. This is a so-called non-moving collector. This is the heap. And now I will show you how it works. So we allocate memory. Objects die. When they go purple, they die. They die fast. And we fill up the heap, right? Everything is clean in front of us. We just allocate memory as crazy. When we run out of memory, we stop the world, mark the objects, remove the rest. Stop, mark, remove, unmark, continue. And you see what happens. Who knows Windows 3.11? Disk defragmentation. Got some memories? This is exactly what we see here. Because we don't move things around on the heap, once you allocate an object, it will stay at that place until it dies. That leads to the fact that if we would like to clean it up, we have to really go through each memory cell to find the dead ones, right? And you see all this cluttering. You can imagine that it's now really hard if I need to allocate, because this is very simplified. If you need to allocate an object that needs 20 memory cells, find the free 20 memory cells in a row. Takes time. If you can't find it, out of memory exception. This is how it works. So this is mark and sweep, and it was used in some collectors. So as I mentioned, fragmentation is the biggest problem. Advantage is we don't have to move stuff around. We don't have to update references. Okay. Leads me to moving collectors. We have two different ones, compacting collector and the copy collector. Let's first take a look at the mark and compact. Pretty much the same, but we have now an additional step, as you can already guess, compaction. So we start allocating. Now we don't fill up the complete heap because we need some spare space to have some temporary space to copy stuff when we do the compaction. So we fill it up right now. We stop, mark, unmark, remove, and now we compact. I hope it's coming again. It's quite quick. But don't care about the numbers. I will explain the numbers in a minute. So we mark, remove, unmark, compact, go again. Biggest advantage when doing compaction is now we have free space ahead of us. Allocation is fast. If the allocation is fast, the application is fast. Okay? This is pretty simple. The faster you can allocate memory, the faster your application will work. Because if the garbage collector allocator has to look for free space, it takes time. So this is mark and compact. We need headroom, depends on the heap size, could be up to 50%. Because when it's full and we start to compact, then we have to find stuff, move it from left to right. So we need some spare place where we can put stuff temporarily. This is probably the drawback of this collector. And then my favorite one, copy collector. And you will see this is different. Now we have two spaces, right? And they are so-called the to space and the from space. And they will toggle. So you will see, once we stop the world, suddenly the gray becomes orange, the orange becomes gray. And the names will also change. The reason is we start allocating in the orange one. And once the orange one is full, we mark everything that is live. And then, and this is now the trick, we copy only the live objects into the empty then to space. And then, this is the big advantage, we can just free the complete space. Because we know everything that's live, we copied out of it, so we don't have to check anymore, okay? Way faster. But you see the problem, we need twice the amount of memory. Right? If you need a 1 gigabyte heap, you in principle need 2 gigabytes here. Okay, so let's take a look at this one. We allocate, objects will die. Once we fill the space, we will stop the world, mark the live ones, copy them over, and then, so now it's happening, stop, mark, copy. Next effect, directly compacted, because it's empty, right? means next allocation is again fast. This one is clean again, stop the world, mark, copy, compact it, continue. This is the big advantage of using a copy collector. Yes, it has disadvantages. First of all, twice the amount of memory. Second, if we copy things around, updating references all the time, okay? So, this is the copy collector principle. Problem with the updating the references is if we have long-living objects, let's say we have objects that live for the whole lifespan of the application, you copy them every time you do a garbage collection, right? Even if you know it will never die, but you keep it, you have to. So that means that's nice, it's fast, it has some drawbacks, but it's a nice principle to get rid of this freeing problem. That leads me to the last one that we will look at, which is generational collection. Who knows what generational garbage collection is? Good. For the ones who don't know, it's not a big deal. There's the so-called weak generational hypothesis. In plain English, most objects die young. That's what it means. So we have the number of objects on the y-axis and the lifetime of the objects on the x-axis. You see we have lots of objects that die very quickly. Then we have a couple of objects that live a little bit longer, and then you have just a few objects that live really for a long time. Now, with the principles that I showed you, we can shape a garbage collector directly for this behavior. So what we do is, we take the so-called Eden space, don't ask me why they choose that name. Only in this area we allocate memory, right? And this is a small area. But because objects die fast, garbage collection is pretty quick in this area, because it's small. Then we have a copy collector here, also known as survivor spaces. Probably you heard that, because objects that survive for a couple of times will then be promoted into the old generation. And yes, the old generation is big. It's bigger than the others. Anybody, any idea why this is the case? It's pretty simple. We just have a few objects that are really old. So that means it takes really long to fill that up. And maybe, if you're lucky, you never have to do garbage collection here. This is the idea behind it. So that means we have the young generation, which is the Eden space and the survivor spaces, and the old generation, which is the blue area here. And we have different garbage collection cycles for them. So we have the minor collection, which is only for the young generation. And we have the major collection, which is only for the old generation. And then we have a full collection that does both. This is the worst case. Because usually it first does the old generation and then the young one. And if the old generation is big, and we use something like mark and sweep here, then it takes a long time to clean this. And this is also one of the problems that we saw in reality. If you would like to see how it works, of course I have a demo. We go first through the cycle. In this example, if an object survives 3 times the garbage collection, I will promote it to the old generation. Let's take a look at that. So we allocate memory, objects die fast, stop the world, mark, copy to the 2 space, continue, remove, continue. Then we go on. And it will be faster once we promote the first objects. And then you will see, even in the old generation, there's some kind of wavefront moving slowly until we fill it up. Because even here, objects will die at some point, right? So let's see. Yeah, now it happens. Now it's faster. Now you can see how that works. And you see the advantages, because long-living objects will just be promoted. They don't have to be copied all the time. This is mark and sweep in this case, or mark and compact, I think. So we stop the world now in a second. So now there's no space anymore. We stop, mark, compact, and then we copy everything from the young generation also in the old generation. And then we start from scratch. This is how very basic generational garbage collection could be implemented, right? There are other ways. Is someone using IBM OpenJ9? Because they have different garbage collectors. They have something similar without Eden. They directly allocate in the copy collectors. It's another way of doing it. Okay, everybody got that? How that works? Not so hard, right? Okay, so now let's take a look at the collectors in the JVM. Because we just have 40 minutes, usually I also explain concurrent garbage collection, but we have to skip it here. So we start with the serial collector, which is the oldest one in the JVM. It was there from the beginning. For each collector, I have this sheet where you can get some properties like availability, is it parallel or not, is it concurrent or not, generational, heap size, small to medium. What does it mean? Well, if you ask me today, might mean 2 gigs to 4 gigs. If you ask me 10 years ago, 512 megabytes to 1 gig maybe, so it really depends, right? It depends because a couple of years back we didn't have microservices, then the whole thing is different. But in principle it means not... So what are the heap sizes you work with? Give me some numbers. 2 gigabytes. Nobody's working with 2 gigabytes, I can't believe it. 1 gigabyte. More than 2? Less than 1, okay. Oh, this is interesting. Someone more than 8? Nobody? More than 32? No? Okay, good. Because this is, then I have something for you. Pause times longer, throughput low, latency higher, CPU overhead very low. And if you would like to use it, this is how you specify it, okay? And this is still a good collector. It's good for single-core systems with smaller heaps, like smaller than 4 gigabytes. And if you don't have any pause time requirements, if you don't care, then this is a quite good one. And who's working with microservices here? Okay, because then I have something for you. Let's take a look at this. If you use a node with just 1 CPU, or if it has less than 1.8 gigabytes of RAM, and you don't specify a garbage collector, you will get this one. It's not G1, right? Why is that a problem? Well, if you start, and you start with 2 gigs, for example, then you get G1. Then a manager came and said, oh, can we do something? The cloud costs are so high. Oh, maybe we can reduce the heap. Yeah, reduce it to 1.5 gigs. Fine. Suddenly, you see stops, garbage collection pauses. And then the reason is because you didn't really specify a garbage collector. Then the JVM will choose serial collector for you. If you specify G1, you will get it. But if you don't do it, you will get this one. And the problem with this one is, you might already see, we just have one thread for the young generation and also for the old generation garbage collection. And this is the reason why it takes long. First of all, it's unpredictable when it will happen. Secondly, because we saw young generation is often, that means it's only one thread doing the garbage collection, takes some time, and this is one of the biggest drawbacks here. Apart from that, it's not a bad collector. Right? It's just you have to be aware that you might get this without knowing it. Leads me to the next one, parallel GC. This is also called the throughput collector. And the reason for that is, first of all, this is fully parallel. That means we just don't use one thread for the garbage collection, but we use as many as possible. If you have more than one, the garbage collector will try, and you can even configure that, to use as many as possible. And that is also the reason why this is called the throughput collector. If you are aiming for throughput, this is the best collector you can get in the JVM. Throughput is defined by time you spent in the garbage collection versus time you spent in the application. And because you have lots of threads available, the time is very short that you spent in garbage collection. Apart from that, it's not really predictable. So there's not really a number that will tell you, oh, garbage collection will take max 1 second. No, you don't know. This is the problem. There was something with the naming in the past, which is a little bit confusing. Let me explain it to you. This is how they started. Young generation, multiple threads in parallel. Old generation, one thread, like with serial. And you switched it on like this. And then someone smart came to the idea and said, we can also do parallel here. Yeah, let's do that. But the problem is they named it use parallel old GC. This is a great name. No, don't use the old one. Use the new one. Then you get the one thread, right? This was only from JDK 5 to 8. So if you're above 8, no problem. These days, there's only use parallel GC and you get this one, right? But there have been some times where both was available, very confusing. That means even if young or old, doesn't matter, we get parallel threads doing the garbage collection, which means this is really very fast garbage collector, very good one. CMS, concurrent mark and sweep. That was the first one that was partially concurrent. Is someone on JDK 11 still, or 8, or below? Nobody? Good, because then you can't use it anymore. This is deprecated, I think, in JDK 9, and it was removed in JDK 13, so it's not available in the JDK anymore. But it was a good collector because it was also the first one where they could more or less guarantee the pauses won't be longer than 1 second, which was not possible with the other ones. Okay, so you will see that the CPU overhead will rise over time because as soon as we start doing something concurrently, means you have 100, let's say, 100 CPUs, right? 100 cores, and you use parallel GC. That means if the application is running, you have 100 cores for your application, then you do garbage collection, in best case 100 threads or 100 CPUs doing garbage collection, and then again 100 threads doing 100 cores doing application work. Here, it's partially concurrent, means we start with 90 of the 100 cores working on the application, and 10 we always need for garbage collection. If we go fully concurrent with the upcoming collectors, it means you can easily lose 20% of the cores just for garbage collection because it's going all the time, right? The JVM not only has to run your application, but it at the same time has to do garbage collection. That means as soon as you go concurrent with garbage collection, you will see a drop in performance. Just keep that in mind. Even if Netflix says they use ZGC, they do. It's a different story. We will come to that. That was a quite good collector. They didn't really continue working on that because first of all, the code was too complex. Secondly, this one didn't use compaction. That was really mark and sweep in the old generation. And that was really a problem because you had a really cluttered heap and then it leads to performance problems in the end. This is how it works. You see some things already happened at the same time concurrently. We don't go through the diagrams because of time. Leads me to the next one, G1. This is the current default collector in OpenJDK, and it's a quite good one. It's called garbage first, and this is different because this is a region-based collector. So instead of having these huge areas of memory, we now have regions, right? They are way smaller. The max region size is 32 megabytes. And so the whole heap will be split into these regions, and you see there's a little table that shows you if you define a heap size of whatever, smaller than 8 gigs, then the region size will be 2 megabytes. Right? So this is set, and there are lots of different parameters how you can adjust all these things in G1. This is how it looks like when it's running. And yes, I also can show you how it looks like if it's running. So we have Eden regions, the yellow ones. We have survivor regions, that's the orange ones, right? And then we have to nerd, this is the old generation, the blue ones. And there's something called humongous regions. Humongous regions are a little bit special. That means, let's say we have 32 megabytes for the region size, okay? And your object is 16.1 megabyte large, sorry. That means it's a little bit more than half of the region size, the object size. You get the whole region. It's directly a humongous region. That also means you lose the rest of the region. Why I mention that, it can lead to problems if your application works with large objects and you have a not really good configuration of G1 region size. It can lead to the fact that even if you think you have enough heap size, you run out of heap space. Just because you lose with the humongous regions a lot of memory that is not usable anymore. In my demo, I don't have humongous. You should get the idea even without. So in this example, I will create 6 Eden regions. Once they fill up, I will take the 2 Eden regions with the most garbage in it, That means if they have most of the garbage, then it's just a few live objects, copy the live objects into a survivor region. And then I can wipe out the Eden regions. It happened already. Then again, fill up the Eden spaces. And you see, I just choose them randomly. It's not really, in reality, it's different. But to give you an idea that the regions are not bound to the type. Right? Once they are cleaned up, I can use them for whatever I need them. In principle, the same idea that we saw with the generational collection, but now split up into regions, which is the big advantage here is the regions are small. That means garbage collection in that region is super fast, okay? And garbage first because we pick the regions with the most garbage and combine the live objects into a survivor region. This is the idea behind it. Okay, that goes on forever, so I have to stop it. This is more or less the same as CMS was, so it is partially concurrent. Pause times should be around 200 milliseconds. Usually they are below like maybe 100 milliseconds, even up down to 50, which is the reason why it's a pretty good collector for most of the use cases. It's fast, it's reliable. It has its sweet spot around 16 gigs. So this is where it performs best. It doesn't mean it doesn't work with 1 gigabyte, right? But it performs best with 16 gigs. Yeah, it's more or less for all use cases good, except very large heaps. It won't work with very, very large heaps. So, good one. Again, partially concurrent. Default collector since JDK 9 can do concurrent marking. Because we didn't look into marking, we will just skip to epsilon. Who knows what this is? Yeah, this is my favorite because this is the no collector collector. This is like doing in C, malloc, but don't do free. Just fill it up. And if it's full, then crash. That's exactly what happens. Well, it sounds really cool, right? Why would you do that? Well, first of all, if you would like to use it, you have to use unlock experimental VM options, right? So just to make sure that you really know what you're doing. But if you know that, and if you know exactly how much memory your application needs, this is the fastest thing you can do. That means no garbage collection at all. But be aware, that's really tricky to find out. Just, you can try to run your application with this switched on. Usually it's like pressing enter, bam, out of memory exception. This is how it works. So it's really, for very small services, could work. And then you really have, you can get the latest improvements for latency or throughput. But usually this is more for testing. If you would like to test your application, if you have specific algorithms, and you would like to test them without the garbage collection stepping in, this is the reason why they made it publicly available, because it's useful, right? Shenandoah, who knows that one? That was invented by Red Hat. Roman Kenke was one of the programmers behind it. It came at JDK 11, and that was the non-generational version. Since JDK 24, we have the generational, and since JDK 25, it's now fully generational and not as a beta version anymore. This is made for very large heaps. Just be aware of that. Every collector that comes now is made for large heaps. Large means 100 gigabyte plus. And if Netflix says they use ZGC, and they do, they blocked about it. Did someone read that? Oh, I'm surprised. Because usually when they do something, then everybody's like, oh, we have to do ZGC, we have to do microservices, yeah. So, this is a fully concurrent collector, right? No stop the world pauses at all. The max pause times are around 15 milliseconds. Usually they are below 1 millisecond, but this is what they guarantee, around 15 milliseconds. That means if you really have applications that are latency sensitive or large-scale systems, then this is a pretty good collector. But be aware that you need really a lot of heap, and you need lots of CPU to make it really work. One example, run that on a Raspberry Pi. By the way, this is the best thing to test microservices, the Raspberry Pi, believe me. If you use nodes with 2 cores and 1 gig of RAM, well, this is a Raspberry Pi. Then you can get an idea how it really works. And that means if you have 2 cores and you use a fully concurrent collector, you lose 1 core completely. That means 50% drop in performance, right? Because we just have 2. One is for garbage collection, the other for your application. That means the more CPUs you have, the better it will work. And the more memory it has, the faster it will be. So this is the reason why you should be careful using these fully concurrent collectors in production. Yes, I think I already announced that. Leads me to ZGC. That's the latest one. And I just would like to skip through because this is more or less a copy of the last one that I have on the list. It's a regional-based collector, as all of them now. They don't have survivor spaces. It's just old and young generation, right? This is all we need. And very much the same. They predict that normally garbage collection pauses are 1 millisecond or below. Sounds great. Be aware, this is fully concurrent. This is really one of these examples. If you have 100 CPUs, probably 80 will be used for the application, 20 might be used for garbage collection all the time. So you will see a drop in performance. Netflix saw a drop of 3% in performance. Netflix is a customer of ours, so I have some knowledge. First of all, they run 1 million JVMs, which is quite a number. What they call a microservice, what you call a monolith. It's huge microservices. The machines they run it on are really big, which is no surprise that they just saw a drop of 3%. Because on these machines, it doesn't really has this big impact. Right? So you have to know this background to really understand the step to ZGC. It makes sense for them. They have also huge heaps. You see the overhead is already 10 to 20%. Throughput, very high. Latency, very low. And yeah, let's skip through. That's the last one. And ZGC is a copy of that one. The algorithm is exactly the same. And oh, what a surprise, we developed that more than 10 years ago. So this was done by Azul. It's part of the Zing JVM. There's a paper available. If you read the paper, if you see the implementation of ZGC, you will see, oh, that's the same, which is fine. Yeah, we skipped through that. I just would like to explain this one, which is the same in ZGC and C4. And it's so-called colored pointers, or we name it the loaded value barrier. In the other collectors, how it works is, we have the stack frame, we have the reference to the object in the heap. If we would like to copy an object in the heap or move it around, what we do is we stop the world. First of all, we mark it. Then we stop the world. Then we copy it. And the new location is stored in the old object. This is how it works in the other collectors, okay? That means we have to keep the old object around until we updated the reference. Once this is done, we can remove the old object. Right? So that means it sounds like, oh, okay, that is so fast. But if you do it with lots of objects, it means you need more memory, right? So in ZGC and in C4, it's different. We have a so-called loaded value barrier. There's a barrier that means before you can access an object, you have to pass the barrier. The barrier is some code that has to be executed. And the forwarding information, we just copy the object and we store the forwarding information off heap, always in the same place. ZGC does the same. So now we remove the object and the reference is still pointing to the old location. The information where to find it is here. And then there's garbage collection threads. They pick up all these forwarding information and update all the references in the background concurrently. So the worst case scenario is we copied the object, suddenly the application decides, oh, I need this object right now. It tries to find it, and it does a so-called test and jump. So it tries to go there, oh, there's no object. So it fails, and then it picks up automatically. So the application thread is doing that. Picking up the new address, fixing the reference, and then access it. So that means even if we copy stuff around, at runtime, without stopping the world, the application will still find the object because the forwarding information is stored off heap. That's if you hear something about colored pointers, that's how it works. C4, pretty much the same. Let me give you one idea. The customer with the biggest heap that we have, 21 terabyte of heap. Garbage collection pause times below 1 millisecond. You don't want to know the CPUs and stuff. It's huge. Yeah, we skip that one. This is the interesting part. Which one to choose? Well, there's throughput, latency, and resource usage. You can choose. Lucky you, you can only choose 2 out of 3. Sorry, there is not the silver bullet here. So if you need low resource usage and very high throughput, sorry, latency won't be low. Right? This is how it works. Doesn't really help you, I know. This might be better. If you really care about pause times, right? So that means you really need low pause times. Then you're on the left side, fully concurrent garbage collection. It also means you have to live with the overhead for CPU usage and resource usage. If you say, oh, I don't care about pause times, could be 10 seconds, it's a batch application, I don't care. But resources are really expensive, would like to save that. So then you're on the right side. Everybody else is somewhere in the middle, and this is what we saw, right? Most of you use G1 and you are happy, but that doesn't mean it's not worth looking into garbage collectors. So you might want to take a look if you're at the border and you have the impression, somehow we might be faster, memory could be better used or something. Take a look at the other ones, right? Left or right besides you. CMS is not really an option anymore. Parallel often is a good choice if you really look for throughput. If you, yes, question.
How should I look for changing the garbage collector or try to tune the one I got?
Okay, the question is, how should I look, changing the garbage collector or tune what I have? Let me give you one example. What is the usual approach that you do, all of you? You see a problem in production. Oh, I'll try more memory. Didn't work. Try more CPU. Works? Oh, fine. This is usually how it works. And this is costly in the cloud. So it's absolutely worth it. Analyzing your problem, really. And this takes some time. It's not so easy to monitor that, but you have to monitor it and then try a different collector, right? It's not that hard. You just switch it, set the heap values correctly. You start with the same values that you have with the other collector, and then you just measure again. And you will see a difference, probably. Could be worse, could be better. So there's no general rule. It's really up to you and up to the application. Do you have lots of memory pressure in your application, or is it not that hefty? That really depends. So I can't give you a golden rule and say, always do this, doesn't work. It's a lot of work to figure that out. It's a lot of monitoring and understanding how your application works. But once you do that, you can really gain something by choosing the right garbage collector, right? So, because we're running out of time, there's an overview. I'm not sure if the slides will be provided. If not, just ping me on LinkedIn. I can send you the PDF with all the information. This is just a table that you can have everything on one view. And with this, thanks for attending. And if you have further questions, just come to me after the session and then we can talk about it. Thanks.